This work was performed by my students, Carlo Alberto, and also co-supervised by Professor Chiara Bertolin and also Andrea Tridello from the Politecnico di Torino, Chao. The last ones for the Regional University of Science and Technology in Norway. This left-hand roster tools. Yes, we need to reshape to. No, it only goes there. Yes, so as we all know, the spinodoid-like materials is quite popular in nature and also it's widespread. So as we can see, it's across many scales, starting from the centimeter scales to the millimeter scales and also to the nanometer scales. We can all observe that these spinodoid-like materials, and also the material morphologies can be different, can be isotropic, can be cubic, can be columnar, and also lamellar. Interesting, right now, the current design methodologies cannot really mimic or cannot really reflect the nature designs. Because as we see that in the nature styles, it really have the multi-scales. We have the large scales, for example, these cavities, and also the small scale features. And if we use the traditional two-dimensional spinodo-like materials designs, it's impossible to capture the nature features. And also, the current computational models is quite expensive. Therefore, in order to tackle the current challenges, our goal is, can we generate hierarchical nature design and predict behaviors at high accuracy, but also at a low computational cost? Now let's look at the information flow, how we developed these methodologies. So first of all, we generate hierarchical spinodo-like structures, and we perform the fundamental element analysis in order to get data feeding into the deep learning neural networks. Simultaneously, we extract the important networks of the spinodo-like materials, and then we convert this network into the graphs. Therefore, we feed these graphs into the deep learning neural networks. Here we utilize the graph neural networks in order to train these and predict the mechanical behaviors. So let's look at the first step, how we generate these hierarchical designs, because it's not quite easy to do that. Currently, most popular method is to utilize the Gaussian random field to generate spinodo patterns. And governing by these three equations, we can obtain the first order spinodo-like structures easily. When chi equal to 0, that means the cavity, and when chi equal to 1, that means it is the solid phase. And these spinoid-like materials mainly governed by three important parameters: the relative densities, wave numbers, and also the limited angles for the wave propagation directions. In the second orders, we're still using the Gaussian random field method, but in these cases, we imported, or we developed two important features, which is called the theta 1 and theta 2. And these two parameters can easily play with the anisotropic behaviors of the structures and also the hierarchical patterns. So in here, the main three default parameters is still relative density, wave number, and limited angles for the wave propagations. Here, the number 1 and 2 represent the different orders. Now let's look at how we perform the fundamental analysis. In here, we still using the commercial the FE software to perform the simulations. Here, materials always assumed as isotropic and homogeneous. The continuum law here we utilize quite a simple laws, perfect plasticities. Here, the Young's modulus is 1 gigapascals. concentration is 0.3, and also the stress, unit stress is 10 megapascals. The plane strain element was used in the simulation, and on the right side, this is the detailed motion details of our simulations. In here, we fixed the bottom, edge, and applied compressions at the top. And here is how we post-process our data. We get the stress strip curves, and we extract the linear response in here in order to get the effective stiffness from the finite element simulations. Now let's look at one of the important the critical part in here is that how we extract the networks in order to compress information from the spinodo-like materials. In here, we have these hierarchical designs, and we're using this seaming process to only get the topologies of the spinodo-like materials. Therefore, only the node and the line connections exist in these skeletons or the networks. This is how we extracted that once. Therefore, after that, we needed to convert these networks to compress information even more to the graphs. Here is the final, results. And in these cases, the node of the graph neural networks corresponding to the branching nodes and the terminal nodes of our skeletons of the networks, and the input node features include the spatial coordinates, x, y, and also the node degrees. For the edge of the graph neural networks, it represents the branch chains of terminals of the terminal nodes, or the input edge features include the indices of the initial and final nodes, length, and average thickness. Now let's look at how we design the graph neural networks. In here, we're using the MATLAB, the 2024A, because we want to customize everything by ourselves. So we do not use popular PyTorch or that's the TensorFlow framework. In here, what we can see is that on these figures shows the general step how we do it. We import, validate our input data, normalize the data, still train and testing data, and initialize the weight and bias. In here, the MPNN represents the massive crossing neural network architectures. In this that's a batch, we perform transfer the informations from the architectures to predict the normalized effective stiffness, compute MSE of each branch, and in this batch, we utilize the Adam optimizer to perform the optimizations. After that, we rescale predicted effective stiffness, evaluate the MSE, R-square of each epoch, and we complete this one epoch works. Then we repeat it. Finally, we get the iterative effective stiffness by using the trained GNN. Now let's look at the details about the MPNN architectures. So in here, looking at this, that's the flow chart, we utilize the two message passing layers, and in here, the information of the nodes represented by the XI, and also the edge features XI is included into the information aggregations. And finally, we're using the differential nonlinear activation functions, below layers, to perform the nonlinearizations. And this flow chart can be simplified by these two equations, which represent how we aggregate informations for the nodes and for the edges. Okay, after we have our methodologies, now we're looking at the result we have. This is the result of what we're showing, that's how the two-dimensional hierarchical laminar design looks like. As a functions of the theta 1 is for the level 1 thetas, and also for the theta 2 for the level 2 thetas, we can easily to get the representative 16 cases to show in here. For example, when we control theta 1 equals to 90 degrees, what we can observe is that the first order, the large cavities, is almost along the same directions, that means the 90 degrees. And by changing the different that's theta 2s, we can easily change the directions of the second order features as we designed. Here we use the laminar designs as the examples because it's very obvious for the observations how see the change. And also here we get the observations on the relationship between the lamella orientations, which we are very interested in. Our eyes has the equations, has the relations to the wave propagation directions. So here is defined by these two equations. Therefore, we successfully to get the result how we design it. Now, we want to understand more, deeper about our designs. First, let's look at the left figures, which showing you one representative case, how the node degree, distributions. Here, the node degree is equal to 1 means the terminal nodes, and node equal to 2 or 3 and 4, this names the branching. 2 years means, let's say, the lines, therefore it's not very interesting, therefore we just, exclude it, and we never ever observe the node degree is equal to 5 in the current generations of the spinodo-like materials. Let's look at the right side. In the left side, we already know that for the node degree equal to 3 dominating designs. But how about the average node degree of distributions? This is the data result for totally 10,000 cases. So as we can see, the node degree normally distributed through the 2 to the 3. And by looking at 3 representative cases, that means when the chi equals to 2.4, 2.7, and 2.9, what we can see is that for the relatively small chi and relatively large chi, the topologies is completely that's different. It shows that's big difference, and this quantitative the results provide very important information for we later on design our graph neural networks studies. And then we want this is previous for the analysis about the designs. Now we want to see how the distributions of the finite element results. So let's look at the left figures. This shows the non-dimensional stiffness and the functions of the relative densities. Here, the relative densities was defined by the ratios. V is the solid phase of the total of the structures over the volumes of the representative elements. So first, by looking at the distributions, we can get conclusions that current our SAM methodologies can provide quite large relative densities from 0.2 to the 0.8. And also the non-dimensional stiffness give quite that's a large range from 0 to the 0.8. However, for the 0.6 to the 0.8, it's quite difficult to see what happens in here. Therefore, for the next step, we non-dimensionalize these relative densities in order to see the clear distributions how it is. So in here, what we can see is that the non-dimensional stiffness of our designs normally, that's generally replicated from the 0 to the 0.5. And also in the 0.75, the frequency is becomes that's minimums. And we choose to represent the cases which at the lower non-dimensional stiffness and quite a large non-dimensional stiffness to see how that the stress distribution is. And by looking at these stress contours, we can get meaningful the result in here is that yes, by putting more materials, taking the load along the load directions, yes, it should be provide higher non-dimensional stiffness, and if it's less materials along the loading directions, the non-dimensional effective stiffness for whole structures would be lower. So this is confirms our studies. Then finally, let's look at the graph neural networks predictions. In here, we choose, let's say, 2 layers and also 3 layers. That means the 2 message passing layers and 3 message passing layers. And also looking at the different training test ratios, data, starting from the 85% to the 15%, 90 to 10, and 95 to 5. Overall, we can get the conclusion is that by increasing the training data set, we can get better predictions as reflected by the R squares. This also reflected in the 3 layers. Simultaneously, if we control the data split ratios at the same, if you increase the message passing layers, yes, it also slightly increase the prediction accuracies. However, due to the computational cost, by using the 3 message passing layers, in here the results what we have, we would prefer, let's say, 2 message passing layers as our preliminary studies. So finally, I want to make conclusions of our study is that first, we have successfully to develop the method to generate hierarchical, spinoidal, mechanical, metamaterials, and this that there is some quite a robust method to achieve it. And secondly is that we can predict the linear behaviors with the compressed informations via graph neural network. So thanks a lot for your listenings and welcome all the questions and remarks.